Hello everyone and welcome to my talk. I am Dimitrios Giouroukis and this is a survey of adaptive sampling and adaptive filtering algorithms for the Internet of Things. This work was conducted at TU Berlin's DIMA together with Alexnder Dadiani, Jonas Traub, Steffen Zeuch and Volker Markl. For us, the IoT is an environment that consists of multiple heterogeneous devices scattered around multiple subnetworks. In those networks, there are also edge devices that are in physical proximity to users, that are equipped with a plethora of different sensors. In order to perform timely data acquisition on top of such an environment, there are multiple challenges someone has to overcome, namely resource heterogeneity, dealing with scalability in the number of nodes, dealing with ephemeral connectivity, and handling a dynamic topology that changes over time. So for an environment as the IoT, which is highly dynamic and changes a lot over time, adaptivity would be the answer, but can a system that runs on top of such an environment intelligently decide on its own when, where, and how often to read from the sensors that satisfy user queries? And can the same system actually decide on its own which events are actually interesting for further dissemination downstream and then to a sink? The main focus of our work is to identify, study, and gather multiple techniques of adaptive sensor sampling that help answer the questions of when and how often to pull information out of sensors. And the second most important part is, again, study and gather multiple techniques of adaptive sensor filtering, where they answer the question of which information is actually worth reporting. Finally, we want to provide a compact taxonomy of our findings, where it's easy to highlight individual strengths, weaknesses, and any assumptions. Let's begin with a naive example of adaptive sampling. On the left-hand side, we have the original price stream of values incoming from a source. On the right-hand side, we have two different sampling techniques applied and their resulting streams. The orange triangle ones represent the adaptive sampling technique, while the blue diamonds represent the fixed-rate sampling technique. This is actually a representative example of having less values but more accurate results. Then a naive example of adaptive filtering. On the left-hand side, we have a static filter applied on a price stream, where actually we see that the reported values are only 3 because their changes are quite significant. But we later see that for the remainder of the stream, there are no more reportings. If we use an adaptive filter technique, we can see that the filter changes depending on the reading that we get every time. That helps us actually report finer grain changes from the original stream. So our work, at a glance, introduce a taxonomy of algorithms that fall into these categories, and for every one of them, provide an overview of their main ideas, their assumptions, their weak or strong points, and any network overhead. We started with 91 peer-reviewed articles from 64 unique journals and conferences, but we ended up with analyzing 19 of them because of our criteria. Those criteria are that there has to be an optimization focus where a clearly defined metric exists in the narrative of the paper. They have to be sensor-centered, meaning that the proposed solutions are applicable or are exclusively running on sensor nodes. Finally, the last two filters with our subjective are that they had to make explicit assumptions where it's easy to follow about their implementations, and there's a clear evaluation scheme of what they did and how they evaluated their findings. We ended up with 3 main categories, and hence the name of the paper. First, we start with adaptive sampling, we move on to adaptive filtering, and we end up with hybrid algorithms that actually combine the two. We will start with adaptive sampling and explaining their subcategories. First, the adaptive rates category, and secondly, the adaptive compression. Let's start with the adaptive rates. Let's first give our running example that will be used throughout every category. We have a sensor network deployed for detecting any speed limit violations. The environment is a highway and the system is a sensor node or sensor nodes equipped with one sensor. Any findings they report downstream. This is for simplicity's sake and to keep the graphics simple. Let's begin with the adaptive rates. A user issues a query where we want samples or pictures taken from the road network where the speed limit is actually violated, but I want the system to do this every 5 seconds. At the beginning, there is nothing happening over a network, but we still sample values every 5 seconds. Let's say that something fast were to happen, like a supercar going through the highway, violating the speed limit by a lot. The 5-second rule that we impose on our query is not fast enough. If we say we wanted to go with half a second, that would be probably fast enough to capture the plates of the car. That means that this clause of the query is not actually needed anymore if we have something like adaptive rates, and our query would be something like this. The main focus of the whole category of adaptive rates is to adjust the sampling rates of the sensor nodes so they match their events that happen in real time. The main advantage is that someone can get accurate incident reports of an event while it happens, since those algorithms sample a lot faster while something is happening. They also default to some default rate where they actually limit the amount of rates so they don't oversample. The accuracy of those algorithms comes at the cost of network and computational resources. Those resources are used while the event is happening. For a detailed review of each individual algorithm in the category, in the right-hand table, you can find more about them in the paper. We will move on to the sampling algorithms about adaptive compression. We begin with another example. Nothing is happening at the beginning, but we sample once every 4 seconds. Our resulting tuple is one value and 4 timestamps. The current timestamp that we sampled and the 3 previous ones that we didn't. This is because this is imposed on us from the compression level on the query. If something fast were to happen on our network, then we wouldn't be able to report it fast enough back to the sink. If for some reason we wanted to change to half of it, that means we would have to sample once per 2 seconds and report with 2 timestamps and the value from the last one. That means that we would get earlier reports of the events at the sink. This is the main focus of the adaptive compression algorithms. They adjust the level of compression of the session signal either based on the event or based on the spatiotemporal correlations that found in the whole system. These algorithms can actually go below the Nyquist rate of sampling. That means they can actually go below the best rate that would be needed to actually get an accurate representation of the original stream. Their advantage is that there are a lot of communication savings that also scale well to high number of sensors or nodes, in a network. The caveat is that these signals need to be compressed and further decompressed, so a decompression scheme needs to be known a priori, and any updates in the topology affect the end result. The algorithms in the category are shown on the left-hand table. Now we will move on to the filtering algorithms and specifically to the 2 subcategories. First, we will start with the adaptive thresholds. We will go back again to our example. We have a sensor network on top of a highway where nothing is happening and we sample every 1 second. We have applied only a very naive filter that has a lower bound of 10 kilometers per second and an upper bound of 40 kilometers per second. We want to know and get reports every time a car speeds and goes higher than the average speed of the network. The first time we get something like an average car going through the highway, not breaking any limits, this thing should be reported. Why? Because it actually is and falls into the thresholds that we defined already. This should also update our threshold and change it to have a lower limit of 50 kilometers per second and an upper of 70 kilometers per second. If the same thing happens again and again, that means that this incident is not exactly important, is not exactly an outlier. So they should not report, the system should not report more than once what we found, or at least more than a lot of times. The adaptive thresholds then should also report something that is happening really fast and acts like an outlier to the whole system. There it should also change the threshold, and this incident should be reported to the sink. This is the main focus of the whole category. Real-time reconfiguration of filtering thresholds. The main advantage is that this happens in real time, so there's no real interaction from the user. Pick a new range from the incoming data and stick with it, or change it depending on the input. The main caveat of the whole category is that it needs actually time and more samples to adjust to any changes in order to gain valuable context from the data. The list of algorithms is presented on the right-hand side table. We will move on to the model-based filtering, where the same question arises again. Should this incident be reported coming from a highway where we actually check for higher than average speed? This time we use a model in order to get an answer of yes or no, this incident should be reported to the sink, where we get some confidence interval. In our case, the model says yes. This is the general architecture found in most of the algorithms, where we have a local model deployed on a sensor node, and a central model deployed either on an edge node that acts as the leader of the neighborhood or acts as the leader of the whole cluster. There has to be some synchronization in order to update the model from the sources or from the sensor nodes to the edge nodes, because the sensor nodes are actually the ones getting any input. So this is the main selling point of the category and the main focus. Use a predictive model to filter data or stop any transmission at all. The main advantage is that there is a reduction in energy expenditure and network transmissions at the same time, and they can be quite domain specific since the models can be quite accurate. That means an event with different characteristics needs a different model. The caveat is that there are strong topology for static, strong assumptions for static topology, and there has to be training costs for those models. Finally, there are more control messages for synchronizing the models between nodes. Again, the algorithms examined on the right-hand table, more of them in the paper. For the final and last category, we will go through hybrid algorithms. There, we did not find any subcategories because of the variety of the ensembles. Hybrid algorithms actually try to answer the main questions at the same time, or at least provide and expose a trade-off. They actually try to answer if an incident should be reported and if I am sampling it fast enough at the same time. This is like combining adaptive sampling and adaptive filtering in one framework. This is the main focus of this category, and the main advantage is that it's quite flexible when you want to tune between the two, when you want to have better efficiency instead of accuracy, or you have better accuracy instead of efficiency. The caveat is that they are harder to deploy and manage because they require a lot of instrumentation, and reconfiguration of one part of the technique affects the results of the other, so there has to be some domain knowledge. The examined algorithms are presented on the right-hand table, and for more of them in the paper. So if I wanted to present some takeaway messages from our survey, those would be that adaptive rates would be really suited for sudden changes, but using more resources. Adaptive compression is really useful when a resource signal is sparse, hence compression is really easy to implement. Adaptive thresholds actually capture importances from the differences. They actually give you context about our difference. Model-based filtering exploits any spatiotemporal correlations found in the stream. And finally, hybrid techniques provide trade-offs and expose those trade-offs between accuracy for efficiency or vice versa. For more insights, please consult our paper. Finally, we would like to highlight that we identified and unified techniques for adaptive sensor data management. We highlighted strong or weak points and gave any future directions. I guess those directions will be good in order to help decide what techniques fit to which use cases. And for more of our insights, consult our paper. We think it's really useful for those. We are really happy to hear your questions later, and thank you very much.